Hello, my name is Tom Chenevert, Department of Radiology, University of Michigan. On behalf of the Michigan Alzheimer's Disease Center, I'd like to give a podcast about MRI Basics. My target audience is residents, primarily neurology. I consider them the future consumers of MRI. My objectives are to describe the source of our signal, spins, magnetization, resonance, signal detection, and most importantly, the source of our MRI contrast, and lastly, how to form the image. The most basic component of MRI is spin. Spin is a nuclear property. It's like a magnetic bar or magnetic moment, but without an external magnetic field, that magnet will point in arbitrary directions. The moment that magnetization or that magnetic moment is in a magnetic field, it will now precess, much like a spinning top on the floor. What's most important is that the rate of precessional frequency is directly proportional to our magnetic field. And this one expression here is really the primary basis of MRI. Now, we don't make images of single spins, single nuclei. It's really the aggregate of a very large number of spins, nuclear spins in our tissue. And it's essentially the average direction, the average polarization of the aggregate of all those spins that we will use to make our signal. That macroscopic magnetization, the net magnetization, the average of all those little magnetic moments is pointing with our external magnetic field. More importantly, it's proportional to the strength of the magnetic field. So if you have a very strong magnetic field, you'll have a greater degree of polarization of the magnetization. Now, it turns out that when that magnetization is pointing with the magnetic field, it's at equilibrium. We cannot detect that signal. What we have to do is apply another magnetic field. It's called a radio frequency field, or an RF field. What's most important about that is that it's oscillating at the exact resonant frequency, the precessional frequency of our spins. We know that precessional frequency because we know how strong our magnetic field is. What that RF field, that additional magnetic field is, it will tip the magnetization away from pointing with the large B0, the large magnetic field, and now it's detectable. The mechanism of detection of that signal is basically just a receiver coil, a loop of wire near that macroscopic magnetization, that large green magnetization that we had polarized by our main magnetic field. This effect, this Faraday's law of induction, is identical to how we generate electricity by rotating a magnet near a loop of wire. I've slowed things down quite a bit. The RF frequency and the precessional frequency that we're looking at here is really tens to hundreds of cycles per second. Okay, what's the source of this spin? What is the nucleus? We can do MRI, we can do NMR, nuclear magnetic resonance, on a long list of nuclei, but the nuclei, the one and only nuclei really, essentially, that we'll be looking at in MRI is the most simplest. It's the hydrogen nucleus. That is one proton. We don't have free hydrogen in our bodies, but we do have hydrogen nuclei attached to oxygen in the form of water, or the hydrogen associated with a long lipid chain. It is these nuclei, these hydrogen nuclei in these molecules, that is the source of our signal. We are not detecting these protons that are in the oxygen nor in the carbon. That's a different nucleus. The only nucleus that we're detecting with MRI is the hydrogen nucleus. We use loose terminology. When I say we're making an image, I may say we're making an image of the protons. I may say spins, hydrogen, water and fat. That's basically the source of all of our signal. There's one other, and it's silicone. Sometimes we'll do breast imaging looking for silicone. But in essence, this is what we'll be making our images of. Now, what is the source of our contrast? Here's a standard MR image of the brain. We see white matter is relatively bright, gray matter is a little dimmer, and fat is quite bright. CSF in the ventricles is quite dark. We can take these images and completely reverse the contrast. Now, I'm not using the computer. I'm not merely adjusting things synthetically. This is the range of contrast that we have in MRI is really controlled by the biophysics of how we're timing our acquisition and what the tissue is giving us. So the source of contrast really is inherent to the tissue. In a word, the source of that contrast is referred to as relaxation. And it drives nearly all of the MRI contrast that we exploit. Relaxation is briefly described here. Spins are fully polarized by the magnetic field, and that's very quick. It's just a few seconds. And as I said, that magnetization is at equilibrium. It does not generate any signal. We tip that magnetization away. Now we're no longer at equilibrium, and we are able to record a signal, but that signal decays away very quickly, usually just a few tens of milliseconds. It depends on how we're collecting the data. At the same time, that magnet is still turned on. It is repolarizing the magnetization back towards equilibrium. So these two effects, how long the signal persists in your recording, and how quickly that magnetization recovers after being disturbed by our radio frequency pulse, is relaxation. These are on different time scales. So how long the signal persists usually is a few tens of milliseconds, and how long it takes signal to recover, maybe seconds long. Relaxation is, in a word or in a phrase, it's the system returning back to equilibrium. We use times, T1 and T2 times, to describe this, the level of this time scale. T1 is the time scale for a given tissue to repolarize back to the main magnetic field. I like to say, think of it as the signal recovery time. And for example, fat has a short signal recovery time. In roughly a half a second or so, fat is nearly completely recovered. Fluids, pure fluids, like CSF, vitrea in your eyes, fluid in bladder, cysts, etc., have long signal recovery times, long T1 recovery times. White matter, shown here, gray matter. The point is, different tissues have different signal recovery times, and it's inherent in that tissue. T2, again, refers to the signal persistence time. It's the length of time before that signal decays away. Different tissues, again, have different signal persistence time. We have T2, and there's a subtle difference with this other one, referred to as T2 star. It's a detail that we really don't have to get into here. CSF, or fluids, pure fluids, have long signal persistence times, and white matter and gray matter. So the point, again, is that these relaxation times are tissue dependent. So, well, there is a biophysical interpretation of these different relaxation times. It is that, it's very complex, but it refers to the molecular motions that the source of our signal has, water, relative to other motions in tissues, the proteins, the membranes, the macromolecules. It's the relative vibrational frequencies and mobile frequencies that these constituents of the surrounding matrix that we don't make an image of. It's the relative interaction of our signal source, water and fat, relative to this solid matrix that is invisible, is what controls these different relaxation times. Most importantly, disease, changes in the cellular density, edema, inflammation, necrosis, that is pathology affects the T1 and T2 of tissues. This allows us to detect disease amongst normal surrounding tissues. T1 and T2 are numerical values. They're times, they're time scales, though we really rarely quantify them. We instead accentuate the effect of T1 and T2 by controlling the timing of how we collect the data. You will refer to a T1 weighted MRI, a T2 weighted MRI, a proton density weighted MRI. So since we know that different tissues have different recovery times, T1 recovery times, we can go with very rapid pulsing or short repetition time to accentuate the signal in tissues that have short signal recovery time. So the white matter is relatively bright, fat has got a short T1 recovery time. CSF has a very long signal recovery time, so it's quite dark. Or we can go to the other extreme, a long repetition time. So all the signal of all the tissues are fully recovered effectively, but go with a long echo time. Echo time and TR are machine parameters that we control to change the contrast of the signal coming in. So again, it's the timing of the acquisition that we're using to control the contrast. It is not simple computer manipulation of the brightnesses. There are other ways to amplify contrast. We can alter our radio frequency pulses and the timing and add a few extra pulses to greatly accentuate the contrast. Here I'm changing the type of sequence, so I get much greater gray-white contrast. Or we may set our timing so that we can erase or nullify one of the signals, say in CSF, so that we can see a better distinction between this lesion and this ventricle. I indicate we get water, or we get our signal from water and fat. That's true. But they are slightly different in their frequencies. It's the chemical shift frequency. It's 3.5 parts per million difference in the frequency between water and fat. We can exploit that slight difference in frequency and tune our RF pulses to either allow water, shown here slightly dark, and fat, shown very bright, to allow both of those constituents in the signal, or tune our frequency to erase or suppress the fat signal only. This is done pretty much all the time. Or we can set our RF pulses so that we completely avoid getting signal from the fat and only make an image of the water. Lastly, we can add external agents, exogenous agents. Typically, they're gadolinium-based materials, and those contrast agents change the T1 and T2 in the tissues. So here we have a coronal view of the brain. You may detect some disturbance or some non-normal signal here, but if you give a gadolinium contrast agent that leaks out of a compromised blood-brain barrier, and that agent greatly reduces the signal recovery time of the water in this neighborhood, on a heavily T1 weighted scan, you can really make that lesion jump out. And lastly, we can do computer manipulation of the data. We can subtract images acquired with and without fat suppression, or with and without gadolinium, and we can reformat them to look at them in 3D so that we can accentuate the contrast and make it easy for the radiologist to see a lesion here, three-dimensional view of the breast where we've collapsed the data in the third dimension, and you can really easily detect these small lesions thanks to a little contrast being added, and we can do that dynamically. So there's many ways to manipulate the contrast beyond simply adjusting your TR and your TE. But TR and TE and manipulation of timing are the key ones that I like to point out. Okay, last topic is how do we localize our signal? That first expression, that first equation, indicating that the precessional frequency is directly proportional to your applied magnetic field is the key. We spend a lot of money on our magnets. These are large magnets, and we go to great expense to make them as uniform. So it's the uniform magnetic field as a function of location in the magnet that we spend a lot of engineering and effort and dollars to make that uniform. What that means is the precessional frequencies of the spins is uniform in the magnet. At least we hope it's as uniform as it can be. But if we add more hardware to the system and we adjust the magnetic field temporarily, very short term, just a few milliseconds, we can turn on a linear gradient. And the slope of the gradient is really pretty subtle. It's maybe 1% from one side of the magnet to the other. And now we have different precessional frequencies as a function of location in the magnet. And this fact is the way that we can localize where the signal is coming from. This is a construction picture of prior to completely assembling the magnet. This is the main magnetic field. It will set up a magnetic field. In this instance, it's about it is a 3 Tesla scanner, or 30,000 Gauss. 1 Gauss, or rather a half a Gauss, is the Earth's magnetic field. So this is really a very strong magnet. But here you can see the gradient system. It's another set of coils that insert inside of this magnet. And these coils are pulsed, that is, they turned on transiently in our imaging sequences to control the magnetic field in all 3 directions. So there are 3 steps, the 3 primary steps that we use to localize. We have 3D space. We have to localize the signal as a function of X, Y, and Z inside the magnet. First step is, let's turn on a gradient where the slope or the change in the magnetic field, let's say, is going from the foot to the head. And we changed, and since the precessional frequency now changes from foot to head while that gradient is turned on, we can control our RF transmitter to just the right frequency so that when we're tipping those spins, it's happening only at one slice in the body. That's slice selection. And we have many slices to image, so over this TR period that I referred to earlier, we will really probe separately a variety of slices through the anatomy. And you can sort of see a little bit of T1 recovery happening after these pulses. The next step is, let's say we need now to localize signal in the vertical direction, in the anterior-posterior direction. Well, we turn on a gradient temporarily and we can twist the phase of that magnetization. It's a little confusing how phase encoding works, but it allows us to create a phase twist that changes vertically. There's a lot of ambiguity in here, and I'll refer to that in a moment. And the last step is now we still need to localize in the left to right direction. Well, if we turn on yet our last gradient in the right to left direction, we now have different frequencies. And if we are receiving our signal at that instant, we now have an array of frequencies being recorded, and we can sort out those frequencies to localize things in the right to left direction. Now, these 3 steps are really not happening simultaneously. They happen very quickly independently. That is, we can do one-shot localization to carve out a slice and frequency encode, which is the 3rd step, and that happens very quickly. The phase encoding, however, created that highly ambiguous phase twist that went vertical. Then it turns out that the number of phase encoding conditions relates to, how fine of a resolution do I need in my image? The finer the spatial resolution, the more number of phase encoding conditions I have to go through to make that image. Now, let's get back to relaxation. We have to allow the tissue to relax. We want that certain level of contrast. We have to wait a TR interval between our little phase encoding steps. And that's why MRI may take, in certain sequences, very fast, but in certain other requirements where we need good, let's say T2 weighted contrast or more signal averaging, it may take several minutes to make that image, because between each phase encoding step we have to allow relaxation to complete. The tissue is the thing determining how fast it can relax. There's many, many sequences that we have at our disposal, hundreds of sequences. There are several classes of sequences, though, that we use every day and all the time. All these different sequences are dealing with the trade-offs that we have between spatial resolution. How much spatial resolution do we need to show that anatomy? How long is it going to take to acquire that data? What's the quality? What is the level of the signal to noise and contrast? These four concepts are really, MRI is a great example of a lot of balance of trade-offs between these principles, and that's why we have so many different sequences. We may want to accentuate spatial resolution, or we may want to accentuate contrast, or other requirements of our sequences. Thank you for your attention, and this is part one of a two-part series where I'll talk about the different uses of MRI. Thank you.